Hello class. For experiment 7, we will be studying the static equilibrium of a rigid body. So the physical concepts that we will be studying or focusing on in this experiment are the concept of torque in the context of a rigid body and the translational and rotational conditions of static equilibrium for a rigid body. So let's first look at torque. So if there is a force acting at some point P and having a position vector r with respect to some origin O, it is said to generate a torque, which is called the torque tau due to the force F about the point O. And this torque is given by the resultant vector from the cross product of r cross F, uh, as shown in equation number 1. So tau is equal to r cross F. And the magnitude of this torque is given by equation 2. And the direction of this torque is obtained from applying the right-hand rule in the correct format. So the right-hand rule that you see over here in the figure RHR on the right corner is only a version of right-hand rule, and it can have other versions of it, but we will only use this one over here. So if you look at this, what we have done is we have taken the first vector, which is r, and placed it along our right hand, and the second vector f is placed along the other fingers of the right hand. So then the third vector, which is r tau, which is the cross product of r and f, is pointing exactly outwards from our palm. So keep in mind that the cross product r cross f is order dependent. That is, r cross f is not equal to f cross r. It is equal to the negative of f cross r. Hence, when you are taking the cross product, you should be careful when you place the r, when you place the vectors along your thumb and the other fingers of your right hand palm. Also notice that the angle phi is this angle between r and f. Also in figure 1, you will see phi as this angle over here between r and f. Be careful. Sometimes it's confusing to understand to which angle is phi, because this angle over here is also an angle between r and f, but this is not your angle phi. This one over here is angle phi, as shown in figure 1. It is the angle between your thumb and the other fingers when you are trying to use the right hand rule. Next, we try to understand the figure 1 and equation 2 that we mentioned in the previous slide a bit more. So the figure 1 over here is the same. And as I said before, the phi is this smaller angle between your r and f and not the bigger one. As such, you see over here, phi should be between 0 and pi, and it cannot be bigger. But also be careful, even if it is 0 and between 0 and pi, you should be careful in choosing it in the proper way. Another concept that we look at is the lever arm, which is the perpendicular distance from the axis of rotation to the acting line of your force, which is this line over here. This is a 90 degree. So this lever arm is a concept that we will be using in our actual experimental process for this experiment 7. Now, note that this choice of rotating axis is not unique. You can choose multiple rotating axes, and so you will have, as a result, multiple torques of the force about these different axes of choice. And both the position and the orientation of this axis is not unique, and you can choose whichever axis you want to work with. In fact, what we do is for this experiment, we will in fact choose two different points and two different axes to calculate our torques. Next, what we do is we look at the conditions of static equilibrium for a rigid body. So there are actually two separate conditions. One is the translational condition and one is the rotational condition. The translational condition states that the vector sum of all the forces acting on this rigid body should be zero. And the rotational condition states that the vector sum of all the torques acting on this rigid body should also be zero. So only when these two conditions are fulfilled will a body, that is a rigid body, be actually at equilibrium, that is at static equilibrium. Now this is the experimental setup that we have. What we have over here is this rigid disk. This acts as our rigid body. We have this holes drilled onto this plate, and we put pegs on inside this. Now in the final setup, what you will have a paper on top of this as well, which is missing in this diagram because we wanted you to be able to see the actual setup clearly. So what we do is we put strings on these pegs, and we hang masses from the strings, which act as our forces acting on this rigid disk over here. This rigid disk is set up in a way that it is free to rotate about its axis over here, which is the central peg. And finally, when the rigid body is at rest and static equilibrium, we then find the forces acting on it and the resultant torques acting on it. So in fact, as you can see, there are actually three forces here. One is the F1, which is the one side of the weight. The other weight is F2. But if you think about it, if there are only these two forces acting, then this should move this way. But it doesn't, because this central peg exerts a normal reaction force in the opposite way that balances the force due to these two F1 and F2 forces. So we have three forces acting here, and hence three torques, no matter what reference point we choose. However, it is understandable that some of these torques might be zero depending upon our choice of rotating axis or reference point. So now let's look at schematic plots for measurement 1. For measurement 2, actually, you will have the situation to be simpler because there is only one point considered for calculating the torques. Hence, we talk about only our measurement 1, which is the more involved case. So the key idea is that you have this F1 and F2 forces on your two sides. This is F1, this is F2. What you do is you get this line of action, or the acting lines of these forces, from the diagram on the table that I showed in the previous slide, which is experimental setup. And then you draw these lever arms. So in this picture over here, we have considered this point O as our point of reference or our rotating axis. So we have drawn lever arms with respect to O for the forces involved. In this case, in the second case, we have considered P1 as our point of reference or rotating axis, and we have drawn lever arms from P1 onto our forces concerned. Now, in both cases, the lever arms have the same properties. They are perpendicular to the acting line of the force we are considering. So this lever arm is perpendicular to this. This lever arm is perpendicular to N. And over here, similarly, this lever arm is perpendicular to F1, and this lever arm is perpendicular to F2. Of course, lever arms of forces that's passing through a point is zero, and hence are not drawn. Now, once you have these lever arms, what you do is you multiply with the magnitude of the force, and you obtain the torques as well. Also, for the sake of computing this resultant force F, we have measured this angle theta over here and then used it to find the resultant force F using F1 and F2 through the analytic method. Now, keep in mind that this theta is not the same as the phi that we were talking about before, which over here is clearly shown. This over here is your phi, and this over here is your theta, and they are different angles and not the same. So once you have the diagram and you have measured your lever arms, what you do is you fill up this table for calculating your torques. Now F1 and F2 are given to you in terms of grams. That is F1 and F, the masses hanging from the strings are given to you. What you have to do is then convert it to newtons by, that is force, by multiplying it with the acceleration due to gravity and appropriate units of measurement. So once you have F1 and F2, you can find the normal reaction force N, which is simply the resultant of these two forces. L1 and L2 over here are the lever arms for forces F1 and F2. These will be measured from the diagram, and you will be provided with this with these lengths as your data for this experiment. Ln is also similarly the lever arm for the force N. So once you have all these values over here, tau1 is simply obtained by multiplying F1 with L1, because this is the force and this is the lever arm. You similarly obtain tau2 and tau n by multiplying the corresponding forces with the corresponding lever arms. Now finally you have the percent error, but be careful. Percent error cannot really be calculated in this case. So what we calculate is effectively the percent difference. What you do is you find out that out of the three torques in each of these rows, one for O and one for P1, out of the three torques, one will be zero and two will be non-zero. So you take the two non-zero torques and use these two to find the percent error, similar as to the method you used in experiment number 6 for finding percent difference. So your percent error is simply the percent difference using the non-zero torques out of the three in each of the 2 points of reference cases. So that brings us to the end of theory for experiment 7, and now we will go over to the actual. So now we will talk about the actual experimental procedure. As you see, we are back to the force table that we used in our experiment number 4, but we are using it differently in this experiment. So just like before, first we make sure that everything is properly horizontal using our bubble level thing. Next, if you look at this, there is a metal plate on the top, and this metal plate is put in such a way that it is free to rotate. This is because we want all torques to be acting freely so that it is brought to static equilibrium finally. Also notice that there are two forces over here, and since this is free to rotate, there will be two torques acting which need to balance each other more or less at the end. And there is actually a third force, because you see two forces and this has to be balanced by a third force. And the third force comes from the normal force from this peg on the metal plate. That force will again create its own torque, and in the end what happens is that the three torques work in such a way that they balance each other. Same for the three forces. Now the idea is we will trace the line of action of these forces, and then we will find the resultant force, which we do it in the table and calculate the resultant of these forces, which also gives us the estimate of this third force over here. And finally, for that, we will need to mark the angle between the forces. Now be careful, even though we have angle markings over here, we cannot use that for our angle measurement over here, because we needed to bend these in such a way so that this string over here is perfectly straight, not tilted in upwards, downwards, or any sideways direction. This is because if we have this string not exactly straight, there will be unwanted forces that will create error in our calculation. So what we do, we set this up properly. So then what we need to do is we need to trace exactly below this two strings over here, and also mark the point of contact of this peg with the metal disc over here, which gives us point of action of the third force. So this needs to be done carefully because this is our whole data over here, and we want to do it exactly from top so that we have a vertical view of the correct line. So I trace this string and then the second string over here, and finally I look at the point of action and mark it over here. So that concludes our data process. Next, what we will do, we will take this paper off, and then we'll draw the different lines of force of the different forces acting on it, and then we have to calculate the lever arms and the torque. So now what we have done is we have taken our trace from the force table. We have marked the lines for action of F1 and F2 over here, and we have marked our point of contact of the disc with the peg. We have extended the force acting lines backwards so that they actually meet up at an intersection point. And to get the line of action of the reaction force or the balance force, we simply draw a line joining the point of contact with our intersection point. This gives us the line of action for the normal force. So the normal force acts this way backwards over here, and the actual resultant force acts on the opposite direction, in the outward direction. So now we need to find the lever arms for finding our torques. The actual resultant force is found analytically from the methods discussed before. For that, we need the angle over here. So we need to measure that angle for finding the resultant. And by measuring correctly the angle, it comes up to be about 93 degrees. So we note over here that theta is equal to 93 degrees. So this is the theta that we use for finding our resultant force for F1 and F2. Now we need to find the lever arms for calculating our torques. So our lever arm is simply the perpendicular distance of our acting line for the forces from the point of reference that we choose, or the origin that we choose. So first, our origin is set to O. So we need to find the lines of action for F1 and F2, which are these, and the line of action for the normal force, which is this. And then we need to find the lever arms from O onto each of these. So first, we go on to F1. Now, an easy way of doing that is simply lining up the marking over here with this so that whatever line we get is now a 90 degree, and then drop a normal from O onto F1. And then we repeat the same process for our F2. So this is L1 of about O, and this is L2 about O. Clearly, there is no Ln because the normal force directly passes through the point O. Next, we have to do the same thing about P1. So now we need to find normals from P1 onto the N and the F2. So now that we have done everything with our point O, we now want to study the same thing with respect to a different point of reference, which is point P1. So choosing point P1 as our point of reference, now we need to again find a lever arms for all the forces with respect to P1 instead of the previous case. So first what I do is I draw my lever arm for P1 to the normal force over here. So for that, we make our ruler perpendicular to our normal force, and then take the center of P1 over here, and then draw our lever arm. So this is the lever arm for the force of the normal force for point P1. Next, we need to find the same thing for our force F2. So for F2, again, we find the lever arm. So this is L1 about P1. Now, just to be clear exactly, this is a 90 degree. This over here is a 90 degree. Similarly, for the previous case, we had this as a 90 degree and this as a 90 degree. So for P1, the thing to notice is that F1 is passing through P1 itself. As such, we will have no torque for F1 about the point P1. Now for calculating the torques, we need the lengths of these lever arms over here. These will be provided to you as a data file later on.